Hi class, welcome back to Electromagnetics. So we're going to continue our look at analysis of transmission lines, which we've been doing in this whole section. So today we're going to look at the special case of a short circuit. If we put a short circuit at the end of our transmission line, what does that tell us, or what can we learn from that? First, we're going to do a quick historical background, again, of people that have contributed to the field of electromagnetics in some way. So this gentleman was educated at the Albany Academy. This is where he also ended up working. He was the first director of the Smithsonian. Here is an image of this fine gentleman, and if you don't recognize who it is, this is Joseph Henry. So he was alive from 1797 to 1878. Some of the notable things for Mr. Henry: he made improvements on the electromagnetic design, which resulted in improvements for the telegraph. He developed the first electromagnetic machine, which most people consider this the precursor to the electric motor, which of course Tesla perfected. He invented the precursor to the doorbell. So anytime someone comes to your door and you hear the doorbell, you can thank Joseph Henry for that. He discovered inductance about the same time as Faraday did. The only deal is Faraday really gets credit for it because he was the first to publish. So he published that, but we still appreciate his contribution. And for that, the SI unit for induction, which is how inductors are quantified, is named after him for this accomplishment. So you have so many Henrys of inductance. So we're continuing part 7, transmission line analysis. We looked at some of the characteristics of the frequency domain last time, so now we want to take these tools that we now have on our tool case and look what happens when we short circuit a line in the frequency behavior. So here we are. We got our transmission line, which is these two plates here, and looking at the how this is defined, the short occurs at z equals 0, so we're going to say there's some arbitrary source out here at z equals minus L, some length away. So this could either be two parallel plates we see here, and so we put a shorting plate in between them, or it could be some concentric conductors where we put this like a washer-shaped piece of metal at the end to short those out. Whatever it is, it doesn't matter. The math will all work out the same, and so we need to keep in mind then, as we short this out between the plates, we'll have some V as a function of Z or position, and we'll have some current as a function of position as well. So remember to keep all these definitions in mind as we move forward, so it'll help you understand the math. So by observation, we see that we do have a boundary condition, right? So the voltage at 0, that is where the short circuit is, has to be 0. I mean, if it's shorted out, the two ends of our transmission line are touching, that means there can be no potential difference if we have a conductor between them. So if we apply this then to our solution, V at 0, we had this equation from before where we last lecture where we derived this equation for the wave equation, and we plug in 0, we get 0. Well, if we work all this out, e to the 0 is 1, and so that would mean or imply that B, our arbitrary constant, has to equal to negative A. Well, this is important because then this implies that there is a reflected wave. Remember, because we have, if it has the negative gamma or the negative argument here, that means it's a wave transmitting in the right side direction. And then if we have a positive argument of the E function, that means it's what's propagating to the left or backwards. And so we're saying then if these two equal, then there must be a reflected wave that is the exact equal but opposite of the incident wave that's traveling down our transmission line. And so that being the case, we can plug that in. Instead of B, we'll have negative A, and when we work the trig out, this means that our equation for our voltage then is a trig identity minus 2JA sine beta Z. Likewise, Our current, same thing, just becomes a trig identity, and it's just 2a over our intrinsic impedance times the cosine of beta z. So now if we look at this, we can now transfer back, because remember we're in phasor notation now, so we can transfer this back from our identity like we did at the beginning of the course. We can get the real voltage and current and power, and those will translate back to our V as a function of z and t is 2a sine beta z sine omega t plus theta. Our current, same thing, except with our intrinsic impedance. And finally, we have an equation for our power, which is our amplitude squared over intrinsic impedance sine 2 beta z sine 2 omega t plus theta. And so, the thing to keep in mind is this argument here is likely to be, a constant for any given time. And so, depending on what that constant is, it's going to, affect our modes. And we'll look at that on a graph here in just a second. So here's the graph of those equations. Again, these numbers correspond to those modes that I was talking about for that argument of omega t theta, depending on what where we stop the time. But it's important to note here, so again, this is our x-axis here, so our source is over here somewhere, so this is where the short occurs on all of these. And so as we would expect, this is our voltage on the top. So if it's shorted out, our voltage should be 0, but moving backwards, we'll see that we'll have a wave that's transmitting and one that's going back, and it should be exactly the same. So this is what we call a standing wave. So likewise, if we have down here on the current, if we have a short circuit, we would expect then that our current would be the maximum there, right? Anytime you short something out, you're going to get that short circuit current. And so unlike the voltage, our current starts at the peak of the curve, but again, this is also a standing wave as well. And so corresponding to that omega t plus theta argument, wherever we stop the time or pick our time off at. And so you can see it's out of phase by half a cycle there. So then if we come down to the bottom graph, this is now our power. And note the max amplitudes here, 2a over z naught, and then our a squared over z naught from the equations on the previous page. And so this is a product of these two. So you can see everywhere there's a node, I guess we can call this, or a zero crossing. We're going to have a zero crossing here. So it has twice the frequency, I guess you could say. And then you can see that the product of these two follows these two guys as they're moving forward across there. So from that, we can calculate the average power flow for a standing wave. And so to do that, the standard equation of that is just integrate over one period the power function. And so in this case, our period is 2 pi over omega. So if we flip that over to get 1 over t, it's omega over 2 pi. And so same things, 2 pi over omega is our limits of integration. So that's what we'll integrate our power function for. So we can take from 2 slides back what our equation was for power, and you can see that our variable of integration is time, so we can pull everything out that doesn't depend on time. It'll be a constant, and so we're left with the sine 2 omega t plus theta. And when we do execute this integral, since sine is a odd function, we get 0. And so therefore, we can say that the time average power flow down the line is 0 at all points on the line. So this is a common characteristic for complete standing waves. We're not transmitting any power at this point. So here again, by examining the absolute values of the amplitude, we can see we have a pattern here going on, right? So we've got, this is our voltage, and again, we should have 0 wherever the short is. And as we move back, at negative lambda over 2, we'll have a 0, negative lambda, we'll have a 0, negative 3 lambda over 2. And so this should be true for all cases. Again, just examining the trigonometric functions we had before. And likewise, the current is going to be shifted half phase. So in this case, that negative 4 is where our first 0 is, and then we go half lambdas back again. So 3 lambda over 4, 5 lambda over 4, 7 lambda over 4. And so again, this is pretty standard for standing wave patterns. So we can extend now our analysis a little bit further by examining what the input impedance of our structure is. So again, to do this, we know that our input impedance is just defined as the voltage over the current at the entrance or at the input of our circuit. So we said in that first slide that that's negative L, right? It's all the way to the left. The short was at 0, the source was at negative L. And so when we do, we plug in these values, again putting in negative L into the equation. And when we do, what pops out is this tangent function. So it's J Z naught, the tangent of 2 pi f over the phase velocity times L. So since this is a function of L, we can now graph this on the next page. We'll look at that. And we see here that we have, it's all reactive. Our input impedance is all reactive. And so it's either inductive or capacitive. And it depends on frequency, where we land on this. So you can see the x-axis is our frequency. So whatever frequency we're running at, then we can actually flip this, right? So we can increase our frequency and go from the capacitive to inductive state. This brings up a very interesting idea then. Using this previous graph of the input reactance, we can see then that the reactance of a short-circuited line is cyclic. You know, we saw that tangential cycle where those dashed lines where it starts over, with the first max min occurring at the phase velocity over 4L. So if you went back and looked at that graph on the previous slide, you'll see that that first max min, that first dashed line occurred at the phase velocity over 4L. So this being the case, we can associate min and max with frequencies. If we can do that, we should be able to calculate the physical length, or L, of the short circuit, where it's occurring. And this is actually used sometimes in communication theory with, you know, if you have a transmission line where you're going from one building to the next and it's underground and you think it's got a short in it, when we can run these, sweep these frequencies and then find the max and mins, and it'll give us an idea where we can start digging to find the short circuit and repair it. So for example, in this case, if we're given the information that on a short-circuited line we're experiencing a current minimum at 50.01 megahertz, and then we get a current maximum at 50.04 megahertz, then we should be able to figure out the distance L to the short circuit from our generator or from our test unit where we're injecting this. The way we do that is we just set VP over 4L equal to the difference in these two frequencies, 50.4, the max and the min. And when we do that, we can see, work out the math. It comes out to 3 kilohertz, or not hertz, but 3 times 10 to the 4. And so we know that the phase velocity is going to be basically the speed of light. So when we do that, we can plug that back into this original equation. So we take the L out, and then to the top, or actually we swap the L with the 3 times 10 to the 4 is really all we do, and solve for L. So then L will be 3 times 10 to the 8, which is the phase velocity, over 4, which we had before, times 3 times 10 to the 4 here. We work all that out, it's about 2.5 kilometers. So if we had a line running underground and we knew it had a short circuit, or we suspected it did, and we swept the frequencies and came up with these two min and max, then we could tell them where to start digging to go down the line about 2.5 kilometers, and we should be able to find that short circuit. So it's a pretty handy little trick you can do.